Hello, hi everyone. Thank you for joining us. I'm gonna speak in English, so I guess. One question: who speaks English here? Yes, everyone speaks English. Who speaks French? Yeah, a lot, but not everyone. Great. So we're gonna speak in English. If at any point, we don't hear me. Okay, you're not hearing me, so just have to fix the. So it's our first time running a hybrid meetup. One second. Okay, a second test. Yes. Okay, perfect. So thank you everyone for joining us. We're very excited to have this meetup. It's our first event on site since like 2 years. So it's been a long time and we've been really looking forward to meeting all of you. And so, yeah, thank you everyone for joining. So today we're going to speak about machine learning. And we have two guests with us. We have Mojdeh and Guillaume. We're going to introduce them later. Okay. And so we are starting now, and then we're going to have two talks. So one about machine learning for the industry, and one about model inspection. And then we'll finish the evening with a cocktail. So the idea is to really get to know you, know what you like about our meetups, what you want to see, maybe get to know other people who know about Python and who want to try to use Python. And by the way, we really want to thank Talent.io, who is welcoming us today and who's helping us with the cocktail and the networking, and who has like a really nice venue and is hosting us. So thank you. Okay, so who are we? So we are Pyladies. Pyladies is an international community. You can find Pyladies group in many different countries. So in the US, in Australia, in France, in Africa, and many countries. And so we are volunteers, and I'm running the event with Maria. And we are focused on Python, and not only Python, but also related technologies. And machine learning is a big topic for us. But we're also happy to know about what technologies you like, and if you want to suggest at any time some sort of topics for us to speak about, we'd be happy to welcome any ideas. Pyladies, you can see ladies in the name. So it's first and foremost for women, but also for friends. So not only women, we welcome everyone in the community, but our objective is to make sure that women can learn about Python and meet other people who can help them meet other people and learn about Python. And yeah, so we are volunteers, so we're always happy to get a little bit of help to run the events. And we have a code of conduct. So basically, the idea is that we ask everyone to be respectful and kind. I'm sure that everyone is really great here in the community. We never had any problem, but just want to remind that at any time, if anyone feels like that there is a problem here, just come to Maria or I, or if you are online, like drop a little message in the chat, and we can talk about it with you. And this is our first hybrid meetup. So we are here on site, but we don't want to forget about our friends who are online. We hope that it's going to be satisfactory for everyone. I know it's not always easy to feel welcome when you're online, but we feel like we've been running events online for a long time now, and we don't want to forget about our friends who are not in Paris right now. And you can find us online. So we have a Slack group, Twitter account. We welcome any tweets if you want to drop a message. And we have a YouTube channel where we're broadcasting this event. We're always looking for contributions. So if you are a speaker, or if you want to be a speaker someday, or if you know people who want to give talks, feel free to let us know. As I said, we don't have any money. We're also looking for venues and for help with like providing goodies or food for events, etc. So If you have a company that's interested in helping a community such as Pyladies, let us know, and we'd be happy to get a little bit of help so we can continue running our events. And just a word about Ukraine, because this is a very important topic. We just want to encourage everyone, if you can donate something. We don't want to say like where to donate, but if you want to talk about it later, we're happy to try to speak about it with you. And then now we're going to welcome Joanna from Talent.io, who's been helping us a lot with running this event. Thank you.
Should I come here?
Yes, please, yeah. So you can be in the webcam.
How many people are online? Just to see.
We had 30 people registered.
Okay, cool.
I can tell you.
So welcome everyone. Welcome to the online people. I'm Jo. I'm part of Talent.io. You're currently in the HQ of Talent.io. Who knows Talent.io? Who has heard of us? Okay, a few, not many. Okay, cool. Have you ever used the platform already, or you just know us? You have used the platform? Okay, interesting. Cool. So yes, we're really happy to welcome you. Just very briefly, Talent.io was created in 2015. We started in France, and now we operate in Europe. We're basically a specialized tech recruitment platform. So we aim to help tech profiles find a job that they really love, basically, put in simple words. We focus on software engineers, data, product, DevOps. That's kind of like the main jobs that we focus on. And we want to make it very simple and easy for candidates who sign up to Talent.io to find their job entirely freely and through a very simple process, basically. What I wanted to share with you is, if you're wondering what this QR code is, we basically released a salary report, a tech salary report, in which we studied over 100,000 job offers to basically share insights on salaries today. So based on your location, based on your years of experience, you will have a salary range, as well as remote work trends, the most wanted jobs on the market today, and the most looked after technologies. So if you want to download it, feel free to scan the QR code, and you will just need to leave in your email address to receive the salary report in your inbox. So voila, I just wanted to present Talent.io to you. Let me just run through my checklist. Quick practical comments I wanted to share with you. The toilets are just here, so if you want to go to the toilets during the event, just walk through here. On the left, it's the ladies. On the right, it's the men. In terms of COVID, so we're really happy to have you here. Please be safe. You can wear your mask. You don't have to if you don't want to, but we ask you to obviously stay safe. We will have food and drinks brought to you around 9, so just after the talks. It will be over there, so feel free to enjoy the food and drinks, basically. And we also have a few goodies for you available. Some of them will be where the food area is. And we have some laptop stands that are just behind my colleague, which is filming right now, which are available if you want to. They are handmade, wooden made, so you can just grab one if you want to when you leave tonight. Okay, I think I'm done. If you have any questions about our platform later on, feel free to come and see me. I will be here to meet you all and speak with you. So enjoy and have a good night.
Thank you. Okay, so thank you very much for this presentation. And we're going to start with the first talk today by Mojdeh. I'll ask you to give a little bit of applause for Mojdeh. So we're going to start.
So, hi everyone. For those who don't know me, I am Mojdeh, and first of all, thank you all for being here, and thank you to Maud and Maria for inviting me to give this talk. I am a data scientist in Saint-Gobain Research, Pyladies Paris I was, and now I am in Saint-Gobain at the group level, and it has been 4 years that I'm working in Saint-Gobain. And in today's presentation, I would like to talk to you about machine learning projects within applied in Saint-Gobain. Thank you. And okay, so let's start. And let's start by Saint-Gobain. So if you are not French and you are not my colleague, maybe the name Saint-Gobain is not so familiar to you. So Saint-Gobain is a group design, manufactures, and distributes materials and solutions for constructions, for transport, healthcare, and other industrial applications. And actually the material and the products of Saint-Gobain, we can find them everywhere around us. We can find them in our housing, in our building, in transport, in healthcare, and in infrastructure and industrial application. The group has different regional and global businesses. And in most of the regional or global businesses, in terms of the products, Saint-Gobain is either world second or first, or European first in terms of the products. For instance, in flat glass, the products is world second and European first, and in automotive glass, they are first in terms of their product. Some of the regional businesses might be familiar to you. For instance, Placo is Auvert in France. And beside the global and regional businesses, the group also has distribution centers. Again, Poimpé, you probably seen it in France, CDO as well. So beside these businesses, in the group, we also have research centers. We have research centers all over the world. We have a research center in India, in Brazil, in Shanghai, in North America, in Germany, and in France itself, we have 3 research centers. We have a research center in Compiègne, in Provence, and in Paris. So the role of the research center obviously is to support the business groups and to provide solutions for the business group. For instance, provide innovative solutions is one role that our research centers are handling. And if we talk about the data science team, only in Paris, we have 3 data science teams. The team data and decision science and méthode avancée pour la data science, there are 2 teams located in our research center in Paris. And we have 1 team located at the group level, which is called data analytics. So the teams in our research center, obviously, they are more research oriented. And the team at the group level is aiming to provide data products at the group level. But between these 3 groups, the projects that we are working on is varying a lot because we are working for all the businesses of Saint-Gobain. And the projects that we are working on in terms of data is changing from supply chain optimization to sales, marketing, distribution, e-commerce. We do computer vision sometimes. And of course, we are applying machine learning and AI for our industry and Industry 4.0. So this was an introduction to Saint-Gobain and what we do as a data scientist in Saint-Gobain. And now I would like to just talk about a couple of machine learning thematics for industry. And then I will focus on a project, machine learning project for industry that I have been working on in the recent years, more in detail. So one thematic in working in industry is anomaly detection. For instance, on here we have projects where we are detecting infusible from bubbles, and infusibles are anomalies, and we are detecting. So we are performing that by image processing and deep learning and computer vision. Then another thematic is quality control. So in these projects, by analyzing the sounds, recorded sound and signal processing, we provided as the tool for the operators to perform the quality control. And then another thematic, among others, is where we are trying to analyze our process and reduce on energy consumptions and CO2 generations. So the projects that I'm going to talk about from now on is actually in energy and CO2 savings. And it is called machine learning applied for plasterboard dryers. So let's see how plasterboards are made in Saint-Gobain. It starts with gypsum. So in the first step, which is called calcination, the gypsum is grounded and heated up to 160 degrees in order to get a powder, which is called a stucco. Yes?
Excuse me, what's a plasterboard in
Plasterboard.
Sorry?
Placo in French, but if you're in, I mean, basically what you is, I think plasterboard is.
Okay, sure. I think here it is. Okay.
Okay, so in the first step, in calcination, as I said, we are generating a stucco powder. And then in the next step, which is called mixing, and also in the first step, the aim why we are heating the gypsum and grounding and heating it to 160 degrees is because we remove the water and dehydrate it, and we get the powder. Then in the second step, in mixing, we are adding additives and the water to our stucco to get a slurry. And the consistency of the slurry, of course, depends on the water that you add, the amount of water and the amount of additive that you add, and depends on the specification recipe of the board that you are producing. And then in the third step, forming, the slurry is like a sandwich between two papers, and these papers are allowing us to have the thickness of the board that we want. Then it's cut, and then it passed to the dryer. In dryer, which is our step 4, the boards are heated up to 300 degrees, and the aim is to remove the extended water that we added in mixing from the dryers, and only keep very tiny amount of water, which we call residual moistures, and are critical for the good quality of our board. So then after the dryer, the boards are ready in good quality, and then they are packed and shipped to the customers or the client. So as the name of the project suggests, the project is focused on the dryer. And our aim is to reduce energy consumption and CO2 generations while keeping the good quality of the board and by analyzing the dryer. Why we are focusing on dryer? Because 2/3 of the energy consumed in plasterboard plants is consumed in the dryer. And by itself, dryer is an optimized process. It has a good instrumentation level, and we can extract up to 1,000 of parameters from the dryer. So at the time that we wanted to start this project, we estimated that if we save 1% of energy, and this approximately will be equivalent to 500 kilo euros and 300 tons of CO2. Of course, it was before the current position and the war. But still, if we can save 1% of energy, is a good initiative, and we should do it. So this was our proposal and our idea and our initiative. And they said, okay, great, let's try it in a pilot plan and see if it works. So in a pilot plan, this is the steps that we followed. In the first step, of course, we can extract thousands of parameters, but why do we extract thousands of parameters? So we did data analysis, we talked with the business experts, and from 1,000 parameters that we could use, we only reduced it to 16 parameters that actually can be actionable, and in the plant, they can be adjusted. Then we build the traceability tables, and in order to track our boards from mixer to the takeoff. And why we built the traceability tables? Because first we wanted to extract the parameters for each board, and then we wanted, which is also very important for us, we wanted to relate our online measurements in terms of quality to each board in order to make sure we are performing analysis on a good quality of the boards. Then we build our machine learning model, which predicts the energy consumption based on these 16 parameters. And then we propose recommendations of range of parameters and possible gains based on the most influential parameters in the model. And then we said, okay, we have a recommendation. Let's perform some trials and see if it works or not. So before going further, I would like to focus on a couple of points more in terms of the model and the recommendation and the data. So the first point in terms of data, when we are working with industry, we have recordings from sensors in seconds, in minutes, or in 5 minutes, doesn't matter. But it's time series, and we need to respect the properties of the time series data. So we cannot do train test split like classical machine learning model than when we are doing classification. And we need to consider the seasonality of the data into account. So that's the first point. And assuming that we are working with clean data, so we don't have noisy data, we don't have sensors that is malfunctioning, we don't have sensors that is not calibrated. So all of that points also needs to be taken into account. Then in terms of modeling, we are using a regression boosting model, and we are tuning the hyperparameters of the model on a validation set. In terms of recommendation, what we do is that first we interpret our models by classical interpretation techniques in machine learning on a test set, and which, for instance, we are using SHAP, feature importance, and partial dependencies plots. Then by analyzing the interpretation of the model and also by discussing with the business experts, we decide that, okay, on these parameters that are influential on this model, on the prediction of the model, let's perform further statistical analysis and provide a range of recommendations and also provide possible gains. If we follow those recommendations, what's going to happen? So keep that in mind. What happened in the pilot plan? In the pilot plan, we had our interpretation, we discussed with the business, and then we decided to do some trials. The first trial lasted 3 weeks, then the other 2 lasted 1 day, and the results were successful. So following the recommendation proposed by this pipeline and this framework, they saw energy cost savings. If you pay attention a bit in detail, you can see that, okay, they could save energy in gas, but the electricity consumption increased. And that's normal because, I mean, you reduce your gas consumption, you are increasing your electricity consumption in some other sense. But so it's important to keep into account that when we are talking energy cost, we have to keep in mind the price of the gas and electricity with each country. So for instance, in France, maybe electricity is cheaper, but in UK it's not the same. So the results were successful after the trials. So since then, the recommendation is used in the pilot plans, and the successful major savings have been reported in the last 2 years. So great, we have a pipeline. It's simple, it's not complicated in terms of machine learning. So let's adopt it to other plans. Why not? Let's go for it. But actually, it's not that simple. So we have a couple of challenges that we need to take into account. So the first one, different plans, different source of data. Typical problem when we are trying to generalize in industry in the bigger scope. Another problem, which is actually a real life problem, is that each plan has its own specification. The dryers are different from one plant to another. One plant has a dryer with 2 zones, one plant has a dryer with 3 zones. It can go up to 40 zones. So we need to take that into account. I talked about it, but we have to consider the price of energies and like gas and electricity in each country. And as always, we are working with time series. So time series has its own challenges when we are working with data such as time series. Then important points, we need to think that, okay, we are scaling up. We want to scale up at the level of every plant, plasterboard plant all over the world. But who is going to use our result and how they are going to use it? So that's also very important. And then the last point is that, okay, taking all of those into account, how do we going to generalize our model in order to apply our model at the scale of all the companies of plasterboards within Saint-Gobain? So this was a challenge that we were facing when we decided to scale up. And in order to tackle this challenge, we started with the first step, the data gathering. So with the help of the process experts and the process engineers, we create an audit file as a first step, which is actually very useful for us, in order to gather all the necessary informations from the plants that we need for the modeling. And we try to map those informations into the informations that we use for in our model. So this allows us to have some sort of standards in order to apply from one plant to another one. And of course, when we ask each plant to fill this file, we are supporting them to understand what they need to fill and which information they need to provide. Then we start working on our code, and we try to make our code as generalized as possible. So of course, there are parts of the code that can be generalized. Great, let's make them generalized for all the code. But we have to keep in mind some parts it's plant specific. For instance, how you are calculating energy gas consumption in one plant is totally different from another plant. So it's okay, is plant specific. We just have different blocks that needs to be connected and work together at the end. Then to help our user to use this tool as the best that they can, as easy that they can, we design an interface in order to facilitate the use for our final users, which are process engineers in our case. And we provide assistance and training on top of all of this in order to ensure the quality of the data, in order to ensure the sensors are calibrated, in order to ensure that the dryer has the capacity that the model can be performed for the dryer. And we also provide support for the process engineers, which is also very important, for them to understand how to use the results and also understand how the results. So that's also a very important part of the framework. So this is the overall of framework when we scaled or at the level of different plants in Saint-Gobain. And it is in the process. So this is our framework, and we are in the process of scaling up. So we are starting with one or two pilot plants, and then we are going higher. And our deployment pipeline is as the following for the moment. So we are, as a data scientist, we push our code to GitLab platform, and then we have Jenkins to perform our CI/CD, to build our Docker images, to push it to private registry within Saint-Gobain. And then we are deploying on containers for each plant, and also our app is also deployed on the containers. So this current deployment framework allows us to have data standardization, allows us to have automatic access to input and output, and of course we have CI/CD, we have computational powers, and by using our interface, we are providing easy access to the end users.
How much energy did you manage to save in that first plant?
The energy depends on different plants.
So for the first one, before going to generalization, is your model efficient for that first plant?
For 1 year, we managed to save around 98 kilojoules.
98?
Yeah.
For 1 year?
Yes. And this was only, I think, the first year. So it's not negligible for us. It's still our same. Yes.
Where does the training actually happens? Like, is the model only in the built image that the Jenkins is building, and then it lives in the repository? Or do you have a separation between the application code that lives inside the image and somewhere a model repository like ML?
So the thing is that we are providing the model can be trained on demand. So anytime the user wants to train a model with the new data, with the new parameters, and also the parameters of the model, we give them, this is the parameters that you can use. So you can play with it. You can choose this one or that one. Okay, so it can run on demand. So that's the first one. We don't have a trained model, that we are just use a pickle or on another one in container. And for the moment, we have our model is trained on demand in the same container as our app for each plant.
Isn't that a problem when you need to go back to see what happened? Like, let's say someone in a plant will train a model and then things will not behave properly. Like, how can you inspect what happened?
So it depends how you, I mean, what is the end use of this project. So this project is intended for process engineers. So we are, I mean, at the end we are encouraging, and this is the output of the projects, that okay, we show them you have to analyze the result, you have to understand the result, and then you need to perform trials. So we are not automatically adjusting anything. So they perform the trials, and if they agree with the outcome, then they try to use the model again and again afterwards. So that's one thing. And then how we are checking how much energy they could, I mean, is saved. So basically they have their old process, so they know how much energy they are consuming, and then after a trial they are measuring during the trial how much energy they are consuming, or after using the recommendation.
Okay, cool. Thank you.
Yeah. And so I'm actually coming towards the end of the presentation, so feel free to ask if you have any other questions as well. So the conclusion or the message I wanted to transfer is that it is one thing to develop one project for a pilot plant, but it is another thing to scale up at the level of other companies and full companies in different plants. And one big challenge here was that, and that was the interesting point, at least for me, to scale up to at the level of other plants. And of course, I'm not alone in this project. This project is the work of a team. And as Steve Jobs said, yes, great things never happen by one person. There is a team behind. And here we have process managers, we have process experts, we have process engineers that are giving us inputs. We have sponsors, project leader, managers, and we have our IT, MLOps, DevOps, and data engineers. There is a full group behind it. So I'm happy. Yes, go ahead.
I'm just wondering, what is the modeling language you use?
Python.
Only Python. Did you use C++ or other?
No, just the app is in Django.
Okay.
Yeah.
What about your mean absolute error? Can I have the value that you got for the test?
So
the sets?
So since we are interpreting the results of the model, so if first we check the training spreading R2 score of the model on the energy consumption, and then on a test set, for instance, if it's below 80%, we don't consider that, or below 75%, we say okay, there is a margin here, and when you are interpreting the results, be aware that okay, is not as high as we wanted to. So this is something that, but it's the outcome of the model is based on the interpretations of the model on the test set.
Okay.
Yeah.
And just last question: what library did you use?
For which part?
For the modelization part,
So for the model, we are using. We are using Cat Boost Regressor.
Okay.
Yeah.
Thank you.
So thank you. I want to thank all the team members that couldn't be here to present today, but yes, this is a team effort, of course. So before to go to question and answers, again, I would like to say that we are hiring as data scientists in SGR Paris. And if you are interested to work in variety of projects, feel free to check the offer or talk to our chef de group, Marion Perrodin, which is here. And so that's it for me. And thank you for your attention. If you have any other question, feel free to ask.
Only, or does it help you in the further analysis in some?
So yes, we use SHAP summary and SHAP, and we use, for instance, partial independency. We check the predictions of the model and the behavior of the model, and we know that what we are explaining is the behavior of the model. So we know that we are not explaining any causality in terms of the data. So that's clear for us. But this allows us to have discussions based on the interpretation of the model with process experts, and then select a couple of parameters and go check them further. So it allows us to go to that step that, okay, let's check these parameters and perform some statistical analysis on that.
If I understood correctly, you're training a model to just estimate the power consumption of the dryer.
Yes.
And how do you account for the fact that you want to keep a constant quality in the cluster board that you're drying?
We have on our plasterboard lines, we have online measurements about the humidity and temperature of the boards when they are exiting the dryers. So we have those measurements, and that's why we build our traceability steps in order to be able to relate those measurements with each board, because the boards start from the mixer. So in this plan, we are tracking each. So from the mixer, okay, we have a measurements at the end of the line for humidity and temperature, and then we actually make it a product-centric table in order to track each board and to relate measurements to each board. So we relate our measurements at the end of the line in terms of quality to each board. So we know that a good range of products are within this range of information. So we are capable to ensure that, okay, we are performing our analysis on the good quality of boards.
Okay, so you haven't tried to integrate the quality into the loss of your model?
No, this is something that we like to do probably in the next step.
Cool.
Yeah.
I see another question.
Can you talk a little bit about how do you go from, let's optimize the user penalty to let's use machine learning? Like, was it obvious, or like just looking deeper into the data and trying to come up with something?
Kame, I didn't understand your question.
I'm interested to how you went from we have this problem, reducing the amount of energy, to let's use machine learning. Like, was it obvious that machine learning was going to give the best solution or something, or like?
I think in general it's Marion. You can correct me if I'm wrong, because Marion is actually my colleague, which is working with me on this projects. But I think it started from the fact that the dryer is a complex process, and we as I said, we can extract thousands of parameters from it. So it was okay. It's complex. Let's try to see if we can understand and analyze it. And of course, I mean it's not that the process engineers don't have any information about the dryer. They are absolutely aware of the dryer, and they know how it works. But in order to use this information, machine learning seems the good approach.
So what is this follow-up, this project?
The follow-up, actually, so we are at the stage to try to improve our scaling up to other plants. And we would like to, so one thing is that this project is within this project, this was the first big data approach for the plant. And then after that, they are standardizing their data. So we are trying to actually transform the data governance as well. And then, I mean, of course, not us, other departments. And at the end, we would like to apply this or give access to this tool to all the plants. So they can have it, they can use it, and they can play with the modeling and try to see what they can find.
That's another question.
I'm just wondering, why didn't you consider deep learning, especially you got data as a time series? I mean, we got the LSTM. Did you try, or did you?
It wasn't really no, we didn't go to this approach because we started early. I mean, it started with conversation with the plant. We were more interested to go and discuss with the plant, try to find the parameters that are important or has effect of, and then at the end, when we are going towards deep learning, I think we wanted to try something to see if it works. Then it worked, and then we said, okay, it works. Let's apply it. Then.
Thank you very much. One last question. Yeah.
So in terms of data, so they already had like quality measurements and stuff that was like automated, or was it needed to like reorganize the way that data was like?
It depends on plant to plant. So some plants, they have these measurements online, some they don't. So actually, when we tried to deploy this to other plants, we had experiments to work with some plants that they didn't have these measurements. And at the end, we said, no, this is a must to have. So if you don't have those measurements, we will not be able to provide good results. So.
Thank you very much.
Thank you.
Yeah.
Okay, we're good.
I don't know if I have some. Yeah, maybe it's better there. I can start? Okay. Hi, so I'm Guillaume Lemaitre. I'm a software engineer in the Scikit-learn Foundations. So just to explain a bit what is the Scikit-learn Foundation, because maybe you don't know. So there's a Python library to make machine learning that's called Scikit-learn. And actually in Paris, so at INRIA, we have a foundation that employs some people to make the maintenance of the project. And the project is open source. And basically we are paid for dealing and communicating with the communities, solving bugs, and basically having new material and stuff like that. Okay, so I'm part of that foundation there. And today I will speak about something that I should present as well in a Python conference in a couple of days, but with some notebooks, which is about inspecting. So we call this inspection in scikit-learn, but actually you can find also explainable AI or interpretations. I mean, these are all things that are around that. And I will speak a bit like in Python, not only in scikit-learn, because I will have something that will come at the end, which is about SHAP. So how many people are data scientists or like working with data? Say most of them. So probably like my two first things, you already know them, but let's see. I mean, that could be a bit fun. And then I will mainly go back to what we are proposing as tools in scikit-learn to explain and interpret models. And finally, I'm not an expert in SHAP because I mean, it's like a few weeks that I look at that. I lead a bit of literature, but that would be interesting to have discussion about that. And have like a couple of thoughts about this. So first thing is how many people does know the book on the left? In English, it's called Limits to Growth. Anyone? Only one person? Nobody knows that? Nobody knows the GIEC report? Okay, so basically this is a Meadows books. So just for the story, is people that in the 70s were, it was consulted by the Club of Rome, I think, and basically understand how in our economy, we should, I mean, how economy will evolve like during the next 100 years, let's say. And they were interesting about like those people in the MIT because they had the kind of modeling things that could say how basically the resources will diminish or how the pollution will go high, and to go like I will come in 2 or 3 slides, but basically what they were saying in the 70s that everything will go down in 2020. So here we come. And do you have any ideas of what is on the right here? These spaghetti things. No idea. I assume if you didn't read the book, then you don't know. But basically, this is a world. Okay, so it's a modelization of the world. So at the end of everything, what we try to do is that we try to predict something with y, and f is the spaghetti things, and then we just put like some x. So then we have different way of what do we put as an x and how we want to use it. But somehow we just come back like, can you just simplify me the words? And then from that simplified word, can I explain actually what I'm doing? Okay. So I will just like give a couple of things more about like what they were doing and then contrast it with what we do usually in machine learning. But if you want to play with these models, so if you read the book, they will tell you, I mean, or if you listen to people, that's a very complex model. So this is true. I mean, there's some spaghetti and there's variable whatsoever, but you have a Python library that does that, okay? So if you use PyWord 3, you can actually make simulations, and is what they were actually intended. So that's my next slide, where they wanted to understand, so they defined the world how it was with like the dynamics, and they wanted to understand how this is working and how it interacts. And they were not interested about predicting the future, actually. What they were interested is about making different scenarios and see how those things are going to work, and making as well like depending on different assumptions. So for instance, we go with some resources in blue and we'll consume them, but what happens if we just plan that we have actually less resources than what we should have, or what happens if we have actually more resources than what we planned? Okay, so they could basically make different simulations, and their first simulation is like how we are now. So basically, this is a thing that tell you that we'll have a peak of pollution and we are not going in a great line right now. And that was from the 70s, okay? So I encourage you to read the book. It's very nice. There's not a lot of maths or whatsoever inside. So this is for everyone. So what is the difference between this statistical model and what we do in machine learning? I mean, like we do predictive modeling, it's just the aims. So here they were not interested about predicting the future. So, for instance, their time resolution when they were doing the prediction was to say at 10, 20 years, okay, it's how the pollution will go. But they're not interested to know what will happen in the 5th of April 2022 and what will be the measurement of the pollution, okay? When we do predictive modeling, usually the first task is to say, okay, from the past, I learned a kind of model parameters. Please, with this new sample or with these new observations, can you tell me precisely what I will get? Okay, and then we have like different type of model to do that. So we have simple models. So for instance, here I have a regression problem on the left with the orange line, which is just a linear model, or I can have complex model, more complex model. So for instance, a gradient boosting, which is the blue line, and I have the same thing with the classification there. And basically, we can have like different type of models that will give like different outcome. And one of the things that was easy in the previous model was that I can make an intervention in my input, and I will see how the model, how the dynamics is varying. And usually, when we have complex model, otherwise, what is difficult to say is why do I get that answer? Why, for instance, this blue point here is categorized as in the red zone and not in the white zone. So here, this is simple things. It's in 2D. I can understand that. But when it's going to multiple dimensions with things which are not really linear, how can I get like a kind of explanation on that? So it's even more difficult when we have a complex model. Okay. So if you have any question at any point, don't hesitate to stop me. Okay. So in terms of explainability or in inspections, I will give like a small like taxonomy or classification of things. So first we have what we call model-specific methods versus model agnostic. So in the first things, I have a linear models. The model comes with a weight because this is how my model is defined. I can look at the coefficients. Those coefficients are just attached to this type of models. Okay, so this is model specific. On the other side, I can have things that I can give like any type of models with parameters or non-parametric. Okay, so random forest and or linear regression. I can just provide it to my explainer and he will just give me back some answer, but it doesn't depend on the model. So for instance, permutation importance, and I will come back on those different methods, but permutation is one of them that doesn't depend on the type of model. It can be applied to any type of models. And then you have two different answers. So one that is either you want to have to understand globally how your model is working, okay, or specifically to understand why did you get that decisions. Okay, so is global explanation versus local explanations. So in general, let's say if you're an insurance company, you will be really interested by that one because you have to explain to your customer why he doesn't get his loan. Okay, so somehow you want to give him this. If you work at a macro space, maybe you are more interested about to see what are the dynamic, which feature have an impact on what part, but like you average basically for all your data sets. And then there's a third part, which is very important and that are usually just discarded at all, which is what are you explaining basically? And one is on one side you can have like if you use SHAP, you are explaining your models. So your model gives you predictions, and then you explain these predictions. So in regards to the mean prediction, basically, but you at any point on the left part, you have the true target. Okay, so you can have the worst model in the world. The only thing that you say is why these things predict. What is the difference between these things and my mean prediction? But I never check if actually the prediction was good or not. Okay. And that's why you have a second part on the right here, where you can actually include these variables, the true y, and you explain your model, and as well, is it giving me a good predictions? So I will, in the method that will come afterwards, don't hesitate to tell me, hey, which one is it of those, and we can check the classification of those after. But basically, people usually forget that having the thing on the left is sometimes not enough because you want as well a model that works well. So you can already, like, you can explain a model with SHAP if you are sure that this is already a good model. If you already doesn't give you good results, you just explain something, but that have a sense in terms of modelizations, but doesn't have any sense of what does it mean. Okay? So before to go in methods, I have like two messages which are very important. So that the first one is if you try to interpret a model, you can always find an explanations. Okay, so for instance, here I just take adult census. So the idea is to classify a person who will earn more or less than 50 kilo euros a year. I make a linear model on the data that are available, and basically I have a balanced accuracy at 0.6, knowing that the random level will be at 0.5. So it means that I have really bad models. But if I look at the coefficient, I can still see something. And I could come with like, oh, basically if you are like trying to interpret things. So for instance, like I have a negative result for the age. So it means that younger you are, less paid you will be. But I mean, is it meaningful or not? We don't know because we are just explaining junk here, okay? So that's like one first thing that you should be aware is like always evaluate your model before to try to explain it. Second thing is association is not causations. So I try to, so this is an example given by somebody from Twitter, and I kind of like his example, so I just copy paste and like take it and try to make it myself. So the idea is usually, sometimes we just take a shortcut trying to explain something, saying that this is you have a causes, while this is not the case. So here, I have 3 data sets that are generating in 3 different ways, okay, that look exactly the same in terms of distributions. And then if I look at the code that generates them, so that's the true generative process. So it's actually sometimes what we try to explain, okay? So it's a bit I mean, this is kind of like where we want to go back, but this is usually never the case, okay? So on the left, what I have is I generated X, and then I generated Y, like given X, okay? In the second case, I first generated Y, and then generated X, given the Y, okay? So that can happen. And then sometimes it's like you have something that you have a variable that you didn't observe, okay? That will have an impact on X and Y. So in terms of causality, the first one, X causes Y, so this is called causal. In the second case, Y is causing X, so it's called anti-causal. Okay, so I can give you an example of, let's imagine that you have altitude and temperatures. Normally, altitude is causing temperatures, okay? But imagine that now I try to predict the altitude given the temperatures. The law of physics didn't change, okay? This is still the altitude that is causing the temperatures. But if I just reverse my problem, I still try to, to predict the altitude. So that would be like the case that I have an anti-causal way. And the Z here is that, for instance, like the law of physics is above the altitude and the temperature, and something else just causes like those things, and I don't observe it. I don't have it in my X here. So actually, I'm just having some observation on some Y, and this is something else that is just like generating those other things. So one important thing is that in terms of causality, those 3 graphs are very different. In terms of probabilities, they are the same. And if I try just to make a linear regression, for instance, with scikit-learn on those data and predict, I will get 3 models which are exactly the same. Okay, and then you don't know anything about like what generated. I mean, if I don't tell you anything about the causality, you cannot know. Okay, so this is where you always need to, when you try to interpret the results, you always need to know, do I know anything about this causality part? Basically, if you know that part, if you know that you have a causal link, then you are fine. I mean, probably you are doing like causal interpretation, and that's fine. If you don't know it, then probably you should be careful about like what you are saying there. So now that I just like tell you be careful, so now I will just present what we have in scikit-learn in terms of like model specific and in terms of model agnostic, and basically I will finish with SHAP because this is something that we don't have in scikit-learn, which is like local explainability. Okay, so whatever we have in scikit-learn is like global explainability, and then we have the 2 model specific, model agnostic, and we have as well this thing that are you measuring like, I mean, paying attention that you predict well as well, or do you just like check the models? Okay, so the first thing that I will check will be linear models, and I already like show a bit before. But so the data set that I use to generate like the figure that will be afterwards is the following figure. So it's a survey about people, where you have like information about the persons, and you have categorical and numerical features. And then what you try to predict is the wages, which is in $, I think. So if I fit a model, so I can have a preprocessor where I will encode the categorical feature with 1 autoencoders. And for the moment, I don't touch the numerical feature. I let them like how they are. And afterwards, I will just use a ridge regressor. So for the one that maybe doesn't know what we speak here, is like it's a linear model with L2 penalty. So we just try to make all the weights a bit homogeneous. Okay, we don't want to have large weights for some reason. So if we try to do this pipeline here, and then we can look at the coefficients, basically, of that model. So that will give us an information on the question that we try to answer is, seeing that the final prediction is just a linear combination of those, is what is the impact of a specific feature on the output, okay? So first, it tells you here, I'm not checking if my model gives me good results, okay? I'm just explaining the final predictions. So this is kind of straightforward. Scikit-learn just provides you a coef underscore, and then you can already start to interpret that. But there is a lot of pitfalls, because we could say, okay, that should be easy. I have all those things. I should just look at, let's say, the absolute values of the coefficient, and then one that have a large bar will have a huge impact on my prediction, and that should be enough, okay? But there is a kind of pitfalls there, and I have like at least 3 of them, and I will just show them. So first thing is scale matter. So I told you at the first try, I didn't scale my data. So I just like fit the linear models, look at the coefficient. So I will get the thing on the left. And then I do the same, but scaling the feature, and you can see that I have a completely different plot, okay? So in the first one, age and experience, that we could expect to be actually like predictive variables, are not so important compared to others, while in the case that I just standardize everything, they are very important, okay? So why this is the case is because in the first case, the value are inside the original like scale, so in original units, and they can have a dynamic range very, very different. So you cannot compare 2 features between them. You can look at one feature at a time, and it has a meaning. So for instance, if I take the value of the age, it means that if I increase of 1 year, I will have a decrease of that many kilo-euros on my results. Okay, so the one on the left, without any pre-processing, I mean like standardization, I can actually like interpret it in terms of units. But I cannot compare age and experience. I could, bad example, but I cannot compare age and marital status, because they are like, one is varying between 0 and 80, the one is a category that vary between like 0 and 4, okay? So it's like comparing apple and pears. When I standardize, I make that everyone have a unit variance and 0 mean. So then I can say, okay, in terms of impact, age and experience have like bigger impact on than other features. Okay, so it's what it means. So one thing as well that we can see from this, that is not about scale, but that is very important about models, is you can see that younger you are, lower paid you have, and then experience is the inverse, which could be a bit like counterintuitive. Sorry. And one of the reasoning that we have as a human usually is that we marginalize the explanation. So we say, okay, if I'm older, I should be paid more, or if I have more experience, I should be paid more. And we think about like one feature at a time compared to the target. Okay, so it's what we'll see. This is a bit like the partial dependence. Well, what we see, I mean, what we expect there. The problem here is that when we see the coefficient is a conditional thing. So what is the impact of age given that all the other features have a specific values, okay? So it's not, you are not, so in our mind, as a human, we just marginalize things. Here you have like other conditions that are all the other features. And whenever you have like a model, you mix like all the variables together. And when you look at one, this is like only like one piece of the answer. The second thing is, and this is very important, just cross-validate whatever you do, because you can have variance. In the plot on the left, I fit basically my model on some data, maybe on the training data, and I have a single point estimate. So I don't know what happens if I just shuffle a bit my variance. Is my model stable or not? I have no idea. And the only way to know is just shuffle your data or make cross-validation and just repeat the experiment. And then you can look at like all those different features, value, and check how they are. And for instance here, so the age and the experience now are on the bottom of the plot, but you can see that actually I have some outliers. So it means that the bar could go until like the negative one, negative parts. So what you can actually, how you can interpret this is sometimes when the edge is very important negatively, then the experience is important positively. And sometimes just by shuffling the data, they just switch, okay? And why this is the case is because edge and experience are just correlated. So my model at some point choose that the optimal model is to give like this high negative weight to edge, and then it needs to compensate the high positive weight to experience, and vice versa, okay? And without running cross-validation, you just have 1 point estimate, you don't have a distribution of those weights, okay? So if you repeat that, you can know about this. Yeah.
Why did you pick Rich and you didn't choose Lasso?
So it's just my next slides.
Oh, okay.
So I could actually, as you say, if I have correlated features, so with linear models is a bit, might be a bit annoying if we want to have like a closer look or understand better and not have correlated feature. So I could just exclude one of the feature. So I can do it manually first, okay? And I will come back after that with the lasso. And here I just like remove the edge. And now if you check, the experience is not anymore on the positive and negative part. It went always positive because now my model doesn't have the edge to compensate basically the other one. So it will just always use positive experience because this is what like give a better weight. So in linear models, you could use linear regression with L1 penalty that will put to zero some of the, some of the weight. So in that case, if I use lasso, it will just exclude one of them most probably. One of the issue with lasso, in terms of if I listen people that work with me, is that the dropping is just completely, you don't make any choice. So it's you can do it like in a cyclic manner. So say I start from like that first feature, but actually there's no, you don't choose. So it could be as well completely random. So there's no reason why to drop that specific feature. So you could come with by the explanation at the end. So let's say this is good if you want just to use a black box and make a feature selection on the go, and you are interested about the prediction. At the time that you make the explanation itself, then you might think, oh, I dropped that thing because it's not useful, but actually this is not the case. You could have probably dropped the other one as well. So it depends. You need to rethink where those things are correlated. So probably you need to first run like a correlation study to understand which feature are correlating and understand what is important for you. So that's why sometimes people that I work with that are people that use a lot have L1 because they work on brain images. There is a lot of voxel and they want to pick up only part of to understand which part of the brain just light up. So you shouldn't have like all the brain. So they use lasso for that, but they also like try to enforce some kind of grouping and stuff like that. While lasso, if you use it like this, it just like choose whatever you want. Yeah.
Is it better to use the both with this model called
ElasticNet? So ElasticNet will just. So ElasticNet will say I need to have a L1 sparsity. So I need to have sparsity, and in the remaining coefficient, I don't want them to be big. So you will just put them like bring them back. I would say you can start already with a ridge. You are already like in a good path. Then if really you want selection, then you can try to have lasso. But let's say the baseline will be a ridge in that case. Yeah.
I was just wondering, does the number of features contribute somehow to the quality of explanation?
You have, I don't know, it depends of your problem. So in that case, more you have feature, more you will use, you will use all those features to make your final predictions. So at the end is like, what is, if you add more and more feature and that they become more and more correlating between each other, then that will be your params, because then you will have things that will compensate each other. And then the only way to fight that is to use some regularizations to fight the curse of dimensionality. But so yeah, somehow it will have an impact. Any other questions? No? Okay.
What is the error rate of your model, I mean, to guess the result of this model, for example?
This model, I have.
You choose a model and you try to
So,
play with the parameters without knowing that the model is correct.
No. Here, if I give you this example, it's because before we checked that I didn't put in my slides, but basically we checked that the model is. So here is some regressions. So the first thing that we do is that we compute the mean absolute errors that will tell us in $dollars what is the average error that we do, but in $dollars. So if we say a person is earning $5 or $50 a year, then if I have an error of $1, if I'm happy with that, I can start to look at it. But then, like, I need to quantify my errors. I mean, that's the first thing that you should do. Okay. So if you already are like, I already have a model that doesn't perform good, that is already at in average $30 for predicting like a salary of 50 kilo, then that's a big issue to try to explain those.
We have a question from YouTube. So what about the interaction terms to tackle non-linearity with simple models?
Non-interaction terms to... Okay, so what I assume here is that you want to get, for instance, a polynomial degree, so you want to multiply two of them, and then you will get a weight for that. So it just means that two feature like if you get a coefficient out of it, it means that basically there is a great interaction between two features that help you to make the predictions. So it gives you an information that you need those two features together to be able to predict well. So this depends on the type of pipeline that you have. I think I have an example of such of pipeline where I make an interactions because I know that it will help me to predict. And if you don't have that, you don't have the coefficient. So you can already pre-process the data, create the interaction, and then like look at those coefficients.
Thank you.
I hope that was the answer. Okay, so now I will look at a second family of models, which are tree-based models. So basically in scikit-learn, we have the work on tabular data. We have like those two type of things. So when it comes to tree, the easy things, if you have a simple tree, is that you can look at it. Okay. If it's going very deep, then you cannot look at it anymore. Okay. So somehow maybe it can give you some information, but the interesting point here is that there's some statistic that you are computing at each node of the tree. For instance, here we call it Gini, but it could be also called entropy, or in regression it could be like the absolute error or like any type of errors. And one interesting thing that you can get out of it is knowing that we try to minimize this Gini here. If I go from the node here to the next node, I can know the drop of the Gini, and bigger is this drop, better will be my decision, basically. Okay. So if I look, and every time I'm in the node, I use one single feature. So one thing that I can do is to just go through the trees and just add up all those different decrees so we call it impurity, but basically of Gini or errors or whatsoever. And I can add them up. So it's what we call the mean decrease in impurity. And it's something that was in scikit-learn for very, very long times. Everybody was using it. And one day we discovered that you should maybe be careful with that. Okay. So since we try to document and give an example, and I will give it here, that to show you, be careful when you are in those cases. These things might be very like dramatic for you. So I took the Titanic data sets, and which is like who survived on the Titanic, and the goal is to predict whether people will die or not. And in addition, to show my point, I added two new variables which are completely random, so not linked to the target. So one that is numerical, that's for a Gaussian distribution, and one that is just like taking from a uniform distribution like 0, 1, 2. Okay, so like 3 categories. So one will be kind of categorical variables, the other one will be numerical. I create a pipeline, so I didn't put the scikit-learn code because that's still making like some lines. Instead, I show like the graphical things that we do, but basically we have 2 preprocessing steps. One that will look at the numerical feature and we'll just impute because we have some missing value there. And for the categorical feature, we just one encode them. Okay, so this is in order to like see categories in the next section. Usually you will apply your ordinal encoder there, but this is just like for didactic programs. And one that we just preprocess those data, we mix them together and we give this to a random forest, okay, which is a tree-based, that is an ensemble of trees. And if we look at the result and you use the features on the importance underscore, the most important features is a random one, okay, the random numerical feature. And then like at that point, you should say, okay, there's something wrong. So why is this the case? Is because the way that we compute the feature importance there is based on the training set. And actually the tree that is a random forest that I trained here is fully grown trees. So my random forest overfits on the training data, okay? And because I compute like the statistic on the training data, it means that at some point the only way to continue splitting like in each tree and to isolate basically the noise, the noise is actually like feed the noise. Okay, so basically what we created is a lot of rules for all the random feature because it's remain only those samples there. So because he used like those things, this thing is appearing very high. If we would have a method, and I hope that we'll have this in the future, that would compute the same statistic, but on a testing set, the random number there will not appear the first one. Okay, because on a new data set, it will be over type of noise. It will not go in the noisy feature that we saw in the training because it will be different things. Yeah.
Just for the last slide, I think you didn't scale the data.
We don't need to scale the data in a
for the decision tree.
Yeah, decision tree or random forest, you don't need to scale the data because what you do is that you do a brute force approach to try all the values. So imagine that I have a body mass between 3 kg and 5 kg. The idea of the algorithm that is under is going from all the weight possible. So that's a brute force, but we do smart stuff, but between 3 and 5. If I rescale that, it will not change any decision. It's just that it's more compact, but I will try all the values between -2 and 2 if it's a Gaussian. So you will try all the possible results. So then it's just like changing the scale in this way, seeing that this is just a linear operation, you will not have any way of change. So you just gain time just to not scale. And that's why you should not as well do one-hot encoder and use ordinal encoder. So that's the first thing here. So I recall we are random thing because we were using the training data to compute the statistic, and that's not good. Second thing is less obvious here, but if you look at the important features, a part of the random one, you will get usually the numerical feature, while all the categories will be much lower. And the reason is because when you have only few categories, the trees will just use them. I mean, you have less choice to cut inside. So one that is isolated, like some categories, and if they were good, it will just stop. Numerical, you have much more choice where to cut. So you will just like reuse and reuse again those things. So this is one of the reasons why, like, you will have an important bias towards like high cardinality. Okay, so this is if you have a mix of numerical and categorical, this one is very not interesting measure. Okay, so how can you save the world? Okay, because here that doesn't work. So I will go to the model agnostic approach and just like directly on the same example show one alternative that can allow to solve the issue, and it's called permutation importance. So what you do in permutation importance is that you take your data, you take one feature, you shuffle it, you predict again, and you check what is a decreasing score? Because if a feature is really meaningful, if I just shuffle it, it will not help anymore making those decisions, and the accuracy will decrease. If it's a random feature, if I randomize it, it will not change anything. Okay, so I will keep the same score. So here you can see that this method here is not only explaining the model, but is also taking care that I have as well a good prediction. I have my y in the. I'm passing the y test. Okay, here in this function, and then you get like the following things. So first, you can see that the P class that was actually 1, 2, 3 because it was the class, first class, second class on the boat, is very important. While in the previous things, it was on the bottom, like you have the first class that was a bit higher, but I mean, it was very far of the fair and the edge. And here, this is like the second most important things, okay? So that's kind of interesting. Then, as well, an interesting part here is that you can provide this, a training set and a testing set. So you can, if you pass the training set, you would explain what you saw during the training, okay? So that's, if I see the plot on the left, is actually, I can explain a bit more my model, while on the permutation on the test set is just like, is it going to apply the same rules for future data? Okay, so you can check those two things. And for instance, on the left one, you can still see that the random numbers, numerical feature, the tree still use it, okay? So we see that is not to 0, so we still have a small decrease of accuracy because our tree used this for making prediction on the training set. And when we pass on the testing set, then it should be around 0. Okay, it's here, so it's aligned to the 0. If I have more permutation, I mean, it will be aligned there. So at least you have this thing that you can use like both things. Okay. So the permutation importance is probably the thing that you want to use instead of the feature importances until that people inside in the scikit-learn community just solve the problem that we have. But still, I mean, this one would be interesting one day because some people show that actually you can go back to the Shapley values or in SHAP if you are under some certain conditions. So we can discuss this around beers. That will take a bit more time. And then, so there is another thing which is quite interesting is like the partial dependence. So it's when you look at one feature at a time, you vary that features, and you look at how y is varying as well, okay? So for instance, what we can see on the left is we have the average occupations, and the value on the left is basically my target. So more I have people, more so here that the price of house, more the price of the house is decreasing. If a house is getting older, okay, the price is increasing. And the interesting part is that we can mix those things together and come back to our two features interacting together, okay? So if two features wouldn't interact together, you would have a kind of like parallel lines in this way. So here we have an interaction because above 2 years, the line are kind of parallel. So it means that the not 2 years, over an average of 2 persons, this feature doesn't have any more importance, and only the house age have the importance. While that when you have a mixed year, so you have an interaction of the two features in the left area. Okay, so that's, it can give you like some intuition how those things are working. However, you should be careful with that because what you observe here is a mean effect. Okay, so it means that I generated for all my data set, I changed all the values. So for instance, if it was the average occupancy, I have my big X matrix. I went for all the 9 and I fix all the value of the average occupancy to first 2. Take all the results, average them, and it gives me 1 point on that line. Okay. So one problem is sometimes the average is giving you false information, and sometimes you want to actually see every individual line. So I will get like a very complex formula. But in short, this is just something that I have 5 features. Actually, I have 6 because I have a random one just for the fun. And here I have some sign, and that will be the interesting part. where I have like an interaction between sine of x1 and sine of x2 plus x3, and x2 equal x3 in that case. So basically, I should have an interaction between those features, which are kind of sine things, and then I have linear interaction on the left. So if I make the plot, which on the right here, so if I take the average, because I have this interaction about sine wave, the average of it is 0. Okay, because I have some that are like in phase and the one that are in counter phase, so the average of that give me 0. So if I look at the partial independence, it will tell me 0. And somehow you would say, probably, this feature x1, x2, x3, they are useless because they don't interact with y. But actually, it's because you didn't look at the individual things. Because at the just because of our formula, we know that they are predicting on y. And the reason is because we are making averaging here. If we look at the individual lines, then we recover the sign and we understand why we have an average of 0. And to make an opposite of the feature x6, which is not used here, then I have straight line everywhere with an average of 0, because basically this one is useless. Okay, and then I have like linear interaction there. So those individual lines are called ICE, I think. But basically, it's just that the partial dependence is an average of those lines. Okay, so we have those two things implemented in scikit-learn. If you want to play with it. So my final 5 minutes. So it's a bit about SHAP. So I'm not an expert. I only read about it like 2 weeks. From 2 weeks ago. So I'm interested to know if people knows as well. I will just mention like the couple of things why people like it and why they are using it. So one of the strong things about SHAP is that people argue that it has a very strong theoretical background. Okay, so this is based on game theory, and there's those nice axiom and property about the values. So just to be brief, so basically what we try to do is to explain what are the difference in the feature that make. So what are the attribution of the feature that explains the difference between the value of my local prediction with the average values. So to explain that, basically this is using the axiom. Basically, this information here is what is given by the efficiency one. Okay, so it means that if I add up everything here, that is the total effect. Okay, then you have like a couple of more things. Axiom 2 is if a feature doesn't contribute, so if it's useless, it should be 0. The symmetry is like if two features contribute the same, they should have equal values. And then the additivity is more an axiom that allows, for instance, if I have things that happen in an ensemble, so on several trees, I can add up all the SHAP values per feature, and basically this axiom tells me that I can do that. Okay. So that's like the theoretical background that people like to say, and usually when you start to read the paper about SHAP, they will tell you, yeah, that's nice. Okay. Then at the end of my slides, I will tell you, be careful about that. So at the end, what you try to do is to explain a local, like one sample. So for instance, so I took that figure from the book of Christophe Molnar, but basically it's like if I want to sell a flat here by just having animals or not. If animals are allowed and with all the other feature fixed, basically I can sell my flat 10,000 euros more. So somehow here I'm trying to see the impact of having or not animals and what is the price on what is the price increase or decrease. But here this is like in terms of attribution, this is not enough because I just fix the two trees and basically like if it was at the first floor and 50 meters square. So I fix already those values, they didn't change. So this is a bit like what partial dependence is doing. And Shapley values is one step further, is to say, actually, I should consider all the combination of features that are possible. So I should not only consider cat or not cat with like 50 meters and first floor, I should consider it with like all the other features being random, or one being a tree and all the others being random, 50 meters square or all the others being random, etc. And these 4 lines are actually what we call the coalitions. So you have basically what you should do is to flip over and over for all the coalitions. You will get a gain every time for increase or loss for your flat. And at the end, if you want to have, you average all of these, and it's telling you what is the effect of allowing or not animals in the price cell. Okay, so that's what we call correlations. The trouble here is that it's working with 3 features. When you have 100 of them, then you need to make a combinatory, which is huge. You cannot compute it, it's not tractable. So you need to get some kind of approximations. And is what SHAP is doing. Okay, so SHAP is doing some approximation of that things that we have at the beginning, and come back with some value that explains the feature, but in terms, I mean, like the thing that we saw before, but by doing some assumption on the data. So for instance, they will assume that the feature are independent, and like by being independent, they can make like this computation more efficient. Okay, so that's what it does. So SHAP is doing, so first you can do local explanations. So if we say on the left here, I can explain, so I don't remember now who was the person, but basically it was one person on the boat, and it explains what is, so here's the average predictions. I mean, the difference between these persons, so if it survives or not, compared to the average prediction. So here is a bit complicated, because sometimes what does it mean to have an average predictions? Okay, so it means here the average predictions in Titanic mean that you are 65% dead. Okay, so basically whatever number you get is the distance between be 65% dead or be alive or dead. Okay, so good luck with that. So in classification, that might be a bit complex. So sometimes people try to like change the reference point to have a meaningful reference point that you can interpret. And if you sum up all those effects on the data set, you can get by to a mean, like a global feature importance. Okay, so SHAP can allow you as well to do those type of stuff. So that's my last slide, and is where I want to add up stuff that are important with SHAP. So first is usually you explain the model. Okay, so you explain the difference of the mean prediction with the prediction that you have at hand. Nothing told you that what you predicted with your model was good. Okay, there's variant of SHAP that are called loss SHAP, or that actually compute like in regards to the loss. So you put the true Y, you go back to be closer to what is the permutation importance. I mean that in that regard. Okay, so that's the first things. Second things, which is more problematic, is so I told you don't compute the true Shapley values, you compute an approximations. The approximation, the way that they are done, can break actually some of the axioms that people really like because the theory stand. Okay, so the problem is like the way that it works is normally you should use like interventional approach to do things, and actually TreeShap is using observational at first, and then people from the causal inference came and say, hey, your theory doesn't stand because you don't have the symmetry axiom anymore. So it means that 2 features are not weighted anymore, even if they contribute the same. So it means that now you have numbers that you might not know what it means. So that's a bit of a problem. I will come back on that because that might be as well solutions. And then the third thing is me being a software engineer. I'm worried. I look at the code of SHAP. I saw how the dynamic is. If you are a data scientist, just say to your boss that you need to give some money to those people that develop that. Because there is one person project in 2017. He's working in Microsoft. Huh? This is very good. But there is a bit of holes in the rackets. Okay. And for instance, when I speak about interventional and observational, is you explainer can change from one to another without telling you, which means that you might expect to compute something that you were sure, and at the end, if you just search a little bit and it switched like methods and it didn't tell you. As a programmer, this is something that makes me jump because I say like, no, no, no. I mean, at least warn me if you do that. So I think that SHAP needs a bit of love, and this is not a problem of the person that programmed it, because as I tell you, there's one person which has 1,500 issues basically on his repo, GitHub repo, and I would not like to be himself. So, however, there's an interesting thing that I could like read last week, which is about people trying to make Shapley values more causal. So, as I said, basically you don't have any causal effect. However, by doing like these observational things, and if you do it in a smart way, so for instance, saying, oh, a feature is actually the cause of another one. If I do my approximations afterwards, it means that basically you cannot change that feature 2 because it depends on feature 1. So for instance, you cannot be a male and, or you cannot have 20 years, you cannot be 20 years and having 40 years of experience. Okay, so basically you age have a cause on the experience. So if I order those, I can use this during my perturbations, and then I can use some type of causal Shapley values, which will give you some information of direct cause and indirect cause. Okay, so that's like quite new. I think it's NeurIPS 2020. This is not yet in the libraries. But this is an interesting thing about, because it can allow you as well to detect fairness. It's, however, this is very important. This is as well like, you need to be super careful, because if you start to put some causal things there which are not causal, then it give you garbage. I mean, that's one of the issues there. And I think is what all I have. Yes. So if you have any questions, I'm happy to answer. No? Yeah.
So sorry for asking too many questions.
No, it's interesting. At least I feel useful, maybe.
So for SHAP, I mean, we can use it more with models built on scikit-learn, or we can use it with other libraries like Keras or
so that's why SHAP is not in scikit-learn, because they have an overview of the full ecosystem. So you can use it in a lot of implementation of gradient boosting. So EJ Boost, you were speaking about CAS Boost as well, I think, like GBM, etc. And then they have as well stuff for deep learning, specific methods for, like, so you will have some deep lift, I think, or something like this, that explain, for instance, for images or for text, and there you just fit like a transform. I mean, they support transformer, for instance. So
it's quite hard to explain a deep learning model.
Yeah, so you can compute those. So you can explain it, because here you will explain your input feature that does like a lot of nonlinear stuff inside compared to your prediction. So you can use it, and you can use it on images and text specifically. They have explainer just for that. I never use it. I'm not doing I'm not doing deep learning, so I cannot say how it works. If it's like, I can tell you that on tabular, I have a bit of concern, but I mean, it's just like only software engineering stuff. Yeah.
One question, that is, so far the implementations of SHAP that I have found are mostly for supervised models like the tree or SVM. But are there any like implementations for unsupervised, like k-means?
The problem, so I assume that it should work. So the thing, like programmatically, you just need to give him to give a prediction function. So if you say k-means.predict, he will use that. Then you need to pass you x. So you don't need even to a y. Okay, so it's just that he will compare that to the mean thing. So it should work, I assume. It's just that he will not use a tree-based approach. He will use a kernel SHAP or like the permutation or the partition things, and it should work. I don't see why. I mean, he can explain that model, because there's no reason why not. But I never tried. I'm doing only supervised learning. Yeah.
So thanks a lot for the presentation. I have two questions.
Yeah.
First one is, so you said there is not a lot of support on the SHAP library.
Yeah.
Do you think it would be possible to include the SHAP library in the scikit-learn?
So I would first answer to that because we spoke at lunch during this. I say we should do that, and then they say no, we should not. When there is no bug, we can. No, one of the difficulties of doing it. I mean, that might be a good idea for us to say, oh, like this, our things are supported. We are sure we can ensure some of the part. The problem is that the SHAP is already like good in the ecosystem, and it supports Keras, it supports CatBoost, it supports like DBM. So at the time that we do that in scikit-learn, then we have everybody say, well, you think it doesn't work with other stuff, and then we need to do that. And we are still 6 people working, and if we take one project, I mean, this one-person project, but I mean, like, we not have enough time to do that. So it's better for us, I'm trying to go there, try to fix a couple of things that we see that doesn't work, and contribute upstream because they already have the users. We can explain better. I mean, we can fix there things there is much more important. And you have a second question?
Yes, some of my colleagues present me a model from Microsoft that is called explainable boosting model. I don't know if you heard about this model.
Yes.
And how do you think about it? How do you compare it with this kind of methods that you show for explainability of classical?
So I never use it. So from what I remember, this is a gradient boosting with one feature interaction every time. So apparently it works very well, at least on the papers. The thing is that then you can explain, I mean, it tried to get the explanation, keep stuff simple. So at the end, I never look at like what type of explanation they are giving you and what is it based on.
So basically, what you say is that the inherent coefficient of the model is.
Yeah, but because this is an additive model, no? This is yeah. So because at some point we're thinking about adding that the GAM. I think this is one of. So yeah, that I don't know enough to tell you if the, I mean, what are the limitations, basically. I would say that's probably like a good thing to investigate because GAM are quite nice. But I don't know, because when we try to, for instance, why I'm looking at SHAP now is because in the scikit-learn documentation, we want to, I mean, we are always annoying people. We want to tell you, hey, actually, you should take care about those because it's a thing that for us, we don't want to re-implement those, but we want to understand that. And for instance, that would be one thing that we should do as well with that model. I understand what are the limitations. But for that, we need first people to make like mistakes and tell us what mistakes they did. And when that we did that, we say, okay, we can write the documentations. So if any of you like knows, I mean, don't hesitate to open a pull request. Fine? Okay.
Just one personal
Yeah.
question. So do you work full time for scikit-learn?
Yes.
Okay. Is it so? How scikit-learn make money? I mean.
Ah, we don't make money.
Okay.
No.
So how do you survive?
Everybody make money on us. That's.
Yeah. I mean.
No. So regarding the foundations, so the way the foundation works is we are sponsored by companies that pays the salaries. Okay, it means this is what we call in French mécénat. I don't know how it is in English, but basically they are giving money, but we don't give them anything back. Okay, we define basically a big roadmap and we discuss to understand the problem of everyone to see if it's aligned with the community, etc. That's. I mean, they have a kind of words because we are interesting. I mean, they are our first users, so we are interesting to understand their problem because it works there. So for us, it's what fund us. But out of that, we don't make consulting or money on the side.
It's amazing library. I use it every day.
So I hope that for something. But yeah. But right after that, during a long time, it was just volunteers work, at least at the beginning. or public money, where basically at INRIA, when I'm working, we have researchers that use them in the research, were allocated some of the budget in research to employ an engineers that were working time inside that. So that's why if you have some boss that have some spare money somewhere, we are taking it if you want.
Final questions? Okay, so let's thank our speakers again.